We'll start in a minute. We'll continue with test 4 review today. Test 4 is on Friday. So I think what I'll do is I'll do a few of the problems so that we can at least see some of the types in each of the sections. And afterwards, if we don't do all of the problems today, I'm sure we won't. But I'll send the answers in an email later today. So this series right here, the terms are cosine of n divided by n squared plus 1. So there's a message about the video being blurry, but I don't know what's causing that. It looks clear on my end. Oh, okay. All right, so this one, cosine of n, this is not an alternating series, but some of the terms are negative and some of them are positive. So what we do know is cosine of n is between -1 and +1. So if we do a comparison test, first we note that -1 over n squared plus 1 is less than or equal to cosine of n over n squared plus 1, and this is less than or equal to +1 over n squared plus 1. So if we determine that this is convergent absolutely, then every absolute convergent series is convergent. So if we just compare this series with 1 over n squared plus 1, so in other words, the absolute value of cosine of n divided by n squared plus 1 is less than or equal to 1 divided by n squared plus 1. And we know that the series 1 over n squared plus 1, we know that that converges. Right? We know that. If we were to compare this series 1 over, where the terms are 1 over n squared plus 1, and compare it to the series 1 over n squared, the p-series converges, and since 1 over n squared plus 1 is less than 1 over n squared, this series converges. But then when we use this to compare it with the absolute value of cosine of n over n squared plus 1, this series converges absolutely, and if a series converges absolutely, then it converges. That was one of our theorems. Okay, so this series converges. Okay, so let's do the next one, and then we'll move on to the next sheet after that. So this series in part F, the terms are 3 to the n times n to the second divided by n factorial. So the ratio test gets used a lot. It's okay if it's used more than anything else. So the ratio test the terms will be 3 to the n plus 1 times n plus 1 squared over n plus 1 factorial. And then if we divide this by 3 to the n times n squared divided by n factorial, that's equivalent to multiplying by the reciprocal of that. So we have multiply this by n factorial over 3 to the n times n to the second. And then we just do the algebra and arithmetic. Okay, so 3 to the n plus 1 divided by 3 to the n, we just get a factor of 3. Rewrite n plus 1 factorial as n plus 1 times n factorial. And then in the numerator, we still have n plus 1 squared times n factorial, and in the denominator we still have n to the second. But we get some cancellations. N factorial divided by n factorial cancels. Notice that one factor of n plus 1 cancels from the n plus 1 squared over n plus 1. So we're going to get the limit as n approaches infinity. Everything is positive, so I'll just omit the absolute values. So we're going to get 3 times n plus 1 over n squared. So that limit equals 0. So that means this series converges by the ratio test, since the limit using the ratio test is 0. Okay, for now we'll bypass these next examples and let's move on to the next sheet and look at some of these. So here it says determine the radius and interval of convergence for each power series. Okay, let's start with part A. We can use the ratio test to find the radius of convergence and also the interval of convergence. In other words, find all of the values of x for which this series is convergent. So the ratio test, the limit as n approaches infinity, and the absolute value of n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the n. Okay, so rewrite n plus 1 factorial as n plus 1 times n factorial. And then x to the n plus 1 over x to the n is just x. And in the denominator, we have n factorial. The n factorials cancel. So we're left with the limit as n approaches infinity of n plus 1 times the absolute value of x. So just think of x as any real number. And if you replace x with that real number, what will the limit of that be? Yeah, it will be infinity. If you pick x to be any real number, well, with the exception of 0, if x is non-zero, then the limit is infinite. So the only way that we can get convergence is if the limit is less than 1, and the only number that we get a limit less than 1 is when x is 0. So that just means all of the terms in the series are 0. Okay, so the interval of convergence is just 0. Radius of convergence, 0. Okay, let's look at part C. The terms in the series are 2 to the n times x to the n, and we want to find all values of x for which that series converges.
Root test?
Yeah, we can use the root test. Can use the root test. Can also use something else. I'll just mention that a little bit later. So the root test, so the nth root of the absolute value of 2 to the nth times x to the nth. So the nth root of 2 to the n times x to the n in absolute value is 2 times the absolute value of x. And this will converge if this limit is less than 1. But 2 times the absolute value of x is unaffected by n. So in other words, 2 times the absolute value of x is the limit. So 2 times the absolute value of x is less than 1, which means the absolute value of x is less than 1/2. And so the interval of convergence from negative 1/2 to negative 1/2 is less than x, which is less than 1/2. What about the endpoints? Well, if you test 1/2, you get 2 to the n times 1/2 to the n. So all of the terms are 1. And if you sum the series where all of the terms are 1 is divergent, right? 1 plus 1 and so on is infinite. What about when x is negative 1/2?
All the terms.
Yeah, this one diverges because it's like adding negative 1 plus 1 minus 1 plus 1. It doesn't go to infinity, but it doesn't go to any finite number either. It just oscillates. So the interval of convergence is open from negative 1/2 to 1/2. And we would say that the radius of convergence is 1/2. It's 1/2 the length of that interval. Another test, I didn't leave room for it, but you could use the geometric. You could think of this as a geometric series. So in other words, 2 to the n times x to the n, you could write that as the term 2x to the n. So if that's has the form of a geometric series, so the absolute value of 2x would have to be less than 1. Or negative 1 is less than 2x, which is less than positive 1. So you would get the same interval of convergence. Okay, let's try how about part G? So the series, the terms in the series are 2 to the n times x to the n divided by n factorial.
Ratio test?
Yeah, why not the ratio test? Okay, so the limit as n approaches infinity. So in the numerator, 2 to the n plus 1 times x to the n plus 1 over n plus 1 factorial. And when we divide this by 2 to the n times x to the n over n factorial, it's equivalent to multiplying that by the reciprocal of 2 to the n times x to the n over n factorial. So if we multiply by the reciprocal, we have times n factorial over 2 to the n times x to the n. So we simplify that expression. 2 to the n plus 1 divided by 2 to the n simplifies to 2 in the numerator. X to the n divided by, x to the n plus 1 divided by x to the n simplifies to x in the numerator. And n factorial divided by n plus 1 factorial, what does that simplify to? Yeah, n plus 1 in the denominator. If you want to write more detail, you can. but we've seen this several times. We can take a few shortcuts. Okay. So we want to know all of the values of x for which this limit is less than 1.
All of them?
Yeah, this is going to be all real numbers. If you pick x to be any real number and take the limit, then it's going to go to 0 because the n plus 1 is getting larger. And for a fixed x value, the numerator is constant. So this limit is equal to 0 for all real numbers x. So the interval of convergence is negative infinity to infinity. I'll just write interval, by which I mean interval of convergence, negative infinity to infinity. And the radius of convergence is infinity. Okay, let's go on to the next page and do a couple on there. If you looked at these functions closely, you'll notice that in each row, we have the same sort of thing going on. We know the power series for 1 over 1 minus x. That is 1 plus x squared plus x to the third and so on. So the series n equals 0 to infinity of x to the n, right? Okay, the one that's the part E one, which is just to the right, y equals 1 over 1 minus x quantity squared. So what do you know about this one relative to y equals 1 over 1 minus x? Anybody know? So I'll just note, if you compute the derivative with respect to x of 1 over 1 minus x, you get 1 over 1 minus x quantity squared. So since we know the power series for 1 over 1 minus x, we can get a power series of its derivative by taking the derivative of the terms in the power series. See what I mean? So the power series, just take the derivative term by term. We get 1 plus 2x plus 3x squared plus 4x to the third and so on. So in sigma notation, we can write n times x to the n minus 1. So let's test that out. When n is 1, 1 times x to the 0 is 1. When n is 2, 2 times x to the 2 minus 1. Yeah, that appears to work. But do you notice something else? Maybe it's so obvious to you that you wouldn't even bother to point it out. When you compare n times x to the n minus 1 with x to the n, Yeah, n times x to the n minus 1 is the derivative of x to the n. So weird how that works. Not really. Okay, what about this one in part I? Y equals the natural log of 1 over 1 minus x. Yeah, if we compute the integral of 1 over 1 minus x, or an antiderivative, we get the natural log of 1 over 1 minus x. So if we integrate 1 over 1 minus x, then we get a constant plus the natural log of 1 over 1 minus x. Okay, so to find a series for the natural log of 1 over 1 minus x, we just find antiderivatives for each of the terms in the power series for 1 over 1 minus x. So we'll get, when we find antiderivatives of 1 plus x squared and so on, we get x plus x to the second over 2 plus x to the third over 3 and so on. And then if we write it in sigma notation, so what do we write?
X to the n plus 1 over n plus 1.
Yeah, if I do it that way, then I should start with n equals 0, huh? Well, we can test it. So x to the n plus 1 over n plus 1. So when n is 0, we get x to the first over x. When n is 1, x to the 1 plus 1 over 1 plus 1. Yeah, so that appears to work. Okay, all of the other triplets follow the same pattern as this first row. So we can do one more, but I'll just reiterate what I said. If you find a power series for 1 over 1 plus x, then the derivative of that power series will be the power series for negative 1 over 1 plus x quantity squared. And then the power series for the natural log of 1 plus x is the antiderivative of the power series for 1 over 1 plus x. Same pattern in each of those rows. But why don't we look at the bottom one? So parts D, H, and L. So how do we find a power series for 1 over 1 plus x squared?
Negative x.
Yeah, we're gonna think of 1 over 1 plus x squared as 1 over 1 minus negative x squared. And then we'll get 1 plus the term negative x squared to the first, plus the term negative x squared to the second, and so on. So then when we do the arithmetic, we get 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth, and so on. So this one is an alternating series. So n equals something going to infinity. It's alternating, so we have negative 1 to some exponent involving n.
So if we start at 0, then negative 1 to the n
Okay, yeah, n equals 0 to infinity, -1 to the n. The first term is positive. And these will be x to the 2n. Yep, that looks like it's going to work. So we note, hey, you might want to verify this in the event that I made a mistake. But if I didn't make a mistake, then the derivative of 1 over 1 plus x squared is equal to this function, -2x over the quantity 1 plus x squared squared. So to get a power series for this function, we just compute the derivatives of the power series for 1 over 1 plus x squared. And we get -2x plus 4x to the third minus 6x to the fifth plus 8x to the seventh, and so on. So in our sigma notation, it's also alternating. And it looks like what?
Start at n equals 0, -1 power n.
N minus 1, and so it's 2n times x to the 2n minus 1. So I want to start with n equals 1, I think.
Is it too late plus one? Oh, I know.
So let's try this. When n is 1, -1 to the first is negative. And 2 times 1 is negative, we get a -2. And 2 times 1 minus 1 is x to the first. So it works when n is 1. When n is 2, -1 to the second is positive. 2 times 2 is 4. 2 times 2 minus 1 is 3. Yeah, I think this one is the one that works. There are ways to re-index the n values as long as you're consistent. But this is one way to do it. Are we all in agreement? Okay, then, so this function, inverse tangent of x, so we remember from earlier this semester that an antiderivative for 1 over 1 plus x squared is the inverse tangent. Okay, so to find a power series for inverse tangent, we just compute the integrals, or we find antiderivatives for the terms in the power series for 1 over 1 plus x squared. Okay, so antiderivatives for 1 minus x squared plus x to the fourth, and so on. We get x minus x to the third over 3 plus x to the fifth over 5, and so on. And then the sigma notation. Well, the denominators are going to have the form 2n plus 1, and so are the exponents. So it's alternating. So I think we start at 0 this time. N goes from 0 to infinity, -1 to the n, and x to the 2n plus 1 over 2n plus 1. Hey, does that work? Yeah, that looks like it's going to work for that one. Hey, let's do a problem or two on the next page. Compute the numerical value of the series where the terms are n over 2 to the n. Ah. It's the one we want. So from 7 part E, that's one of the ones that we did. We have 1 plus 2x plus 3x squared equals the series from n equals 1 to infinity of n times x to the n minus 1. Oh yeah, and what's the function that it's equal to? 1 over 1 minus x squared. So how can we use this function to help us compute the numerical value of this series where the terms are n over 2 to the n?
Well, x is equal to 2.
Okay, I'll rewrite this series. So that it's n times 1/2 to the nth. So think of 1/2 as a particular value of x. So if we can find a function capital F of x so that the series is n equals 1 to infinity of n times x to the n, if we can find a function f that has this power series as its representation, then we'll be able to find the numerical value of this one, because all we would have to do is replace x with 1/2. See what I mean? So how can we use this particular function and its power series to help us?
Multiply it by x.
Yeah, multiply this function by x. So multiply everything by x, we get so this will give us this power series. And when we multiply each of the terms in the power series by x, we get the sum from n equals 1 to infinity of n times x to the n. Multiply this by x, we get x over 1 minus x quantity squared. So this is the capital F of x that we want. So the numerical value then of this series, where the terms are n times 1/2 to the n, can be found by evaluating capital F of x when x is 1/2. Okay, so on one hand, f of 1/2 is the series where the terms are n times 1/2 to the n. But since we have this function that's equal to that power series, just replace x with 1/2 and then do the arithmetic. 1/2, or 1 minus 1/2 is 1/2, 1/2 squared is 1/4, and 1/2 divided by 1/4 simplifies to 2. Okay, so that's the numerical value of that infinite series. Okay, number 9, find a function whose power series representation is x plus x to the third over 3 plus x to the fifth over 5, and so on. So let's give this a name. Let's call it g of x. So is there anything that sort of stands out when you look at the terms in that series?
They look like the integral, but they're not alternating.
Yeah, they're not alternating, but each of the terms reminds me of an antiderivative. An antiderivative of 1 is x, an antiderivative of x squared is x to the third over 3, and so on. So if I take the derivative of this function, I might find a series that is more familiar to me. So this is 1 plus x to the second plus x to the fourth plus x to the sixth, and so on. And we know how to find the function for this infinite series. It's going to be 1 over something.
Is it 1 over 1 minus x squared?
That's the one. 1 over 1 minus x to the second. Oh, maybe I shouldn't have written so largely. Okay, so to find a function for the given series, we just compute an antiderivative of 1 over 1 minus x squared, right? So in other words, g of x will be equal to an antiderivative of 1 over 1 minus x squared dx. So we'll use a trig substitution. So we'll assign x to be sine of u, and dx is cosine of u du. I'm going to run out of space, I think. So replace 1 times dx with cosine of u du. And we can abbreviate a little bit. We've done this before. If x is sine of u, the denominator is 1 minus sine of u squared. And 1 minus sine of u squared is cosine of u squared. And cosine of u divided by cosine of u squared is 1 over cosine of u. But 1 over cosine of u is secant of u. So I'm skipping a couple of steps in there. And then remember what an antiderivative of secant of u is.
Negative cosecant?
How much?
Cosecant?
It's the natural log of the absolute value of secant of u plus tangent of u, plus a constant. Okay, we go back. We want to express this in terms of x. So we go back to our substitution. Create a right triangle to help us out. So x is equal to the sine of u. If u is that angle, the sine of u is equal to x over 1, so opposite over hypotenuse. Secant of u is hypotenuse over the adjacent side. So we need to know what the adjacent side is. So this is the square root of 1 minus x squared. So we're getting there. Secant of u then is 1 over the square root of 1 minus x squared. Tangent of u is x over the square root of 1 minus x squared. So we can write this as the natural log of 1 plus x over the square root of 1 minus x squared. This would be an okay answer, but we can simplify it. Think of 1 minus x squared as the factors 1 plus x times 1 minus x. So this is the natural log of 1 plus x over the square root of 1 plus x times 1 over the square root of 1 minus x. So 1 plus x over the square root of 1 plus x simplifies to the square root of 1 plus x over 1. And I'll go ahead and write it. 1 plus x over the square root of 1 plus x simplifies to the square root of 1 plus x over 1 multiplied by 1 over the square root of 1 minus x. This is I know, a lot of writing, but the square root of 1 plus x over the square root of 1 minus x is the square root of 1 plus x over 1 minus x. So the natural log of the square root of something is equal to the natural log of that something to the 1/2. And then we can bring the 1/2 out front and write this as the natural 1/2 times the natural log of the absolute value of 1 plus x over 1 minus x. If you were to get it to this step, that would be a pretty good answer if you had this on a test. But you can simplify it this way. Hey, we're about out of time. Like I said, I'll email the answers to all of the other ones a little bit later today. And then tomorrow I will send a link for the test 4. And it will start a few minutes before 9 and go till about 10 on Friday. But that's all for today.